All right, you're going to need the slope formula today. All right, slope formula. You're going to need distance. You're going to need the big three here. Distance, and you're going to need midpoint. So I just want to review those right at the beginning before we need them. It'll just save time when they come up. And these are formulas you'll need for the rest of the unit too. This is just not a today thing. All right, slope formula. Anybody remember the letter for slope? M. Yep. So M, you got your change in the y. So y2 minus y1 over x2 minus x1. You can use that if you'd like. I'm going to use a different version today, which we've talked about. I'm going to be doing a lot of rise over run today. All right, rise over run. Distance formula. This is the one with the big square root with a little something underneath it. You got your x's subtracted. And a reminder, it does not matter the order you subtract those x's in there, right? Just plot both of them in, subtract them, square them. Plus, and then we're going to do the same thing for our y's when the time comes and square them. And a reminder here, when you are done squaring, you should not get a negative number underneath. Okay, we should not be getting negative numbers underneath here. And then finally, the midpoint. That's going to be add your x's, divide by 2. Add your y's, divide by 2. There's the midpoint. We're going to be using both. All three of them today. All right, here we go. I got a new type of proof for you now. New type of proof. It's called a coordinate proof. Coordinate. We had indirect last one. Now this is called a coordinate. And the only reason why we call it coordinate, it's on the coordinate grid. Okay, we're going to start graphing figures, improving figures on a graph. So I'm going to let you guys go first and graph quadrilateral ABCD. I'll just give you a warning. Look at point C. Point C is 13.6, so you probably don't want to do one of your old school XY axes that look like that. Okay, you want to make sure you can fit 13.6, 7.9 on there. All right, so go ahead, take a couple minutes, graph quadrilateral ABCD for me now. Make sure you label the vertices with A, B, C, and D. Connect them when you're done. And then we'll talk about how this new proof looks. Just make sure you can fit all the coordinates on there. They're all positive, so it shouldn't have any negative coordinates. All right, ready to roll now. It's asking us to prove it's a trapezoid. All right, prove it's a trapezoid. So I want to remind everybody from yesterday, don't do any statements, reasons, because we're not going to do statements, reasons for these new types of proofs here. No statements, reasons. I'm going to ask somebody now. A trapezoid. I'm not saying isosceles. I just want it to be a plain old trapezoid. There was one and one property only of a trapezoid we learned yesterday. What was it? Not isosceles. I'm not talking isosceles. I just want it to be a trapezoid. So what was the one and only one property from yesterday of a trapezoid? It only had one property. If I know it's a trapezoid, what's the only property it has? Jesse?
Has at least one pair of opposite sides.
That is it. That is it. Right here, guys. That's a trapezoid. So that's what I need to show on here. And can we tell which two sides are probably going to be the parallel sides now that we graphed it? Yeah, probably AB and DC. Now the question is, how do I show they're parallel? That's why I gave you those formulas. Go back to unit 3. If two lines are parallel, what did we know about their slopes? They should have been the same. So that's what we need to show now, is that the slope of AB and the slope of DC are the same. That'll make them parallel. That'll make a trapezoid. All right, no statements, reasons, but we are going to keep this thing highly organized. Step 1, decide what formula you need to use. We decided what formula already? Slope formula. I don't need to see it, but apply it. So let's do the slope, M, of side AB. So that's how I'm going to write that, the slope of AB. Now I'm going to turn it over to you guys. You can do y2 minus y1 over x2 minus x1, or I told you I'm going to do rise over run because it's a heck of a lot quicker now that I have it graphed. So go ahead, find the slope of AB, whether you plug it in or you use rise over run. Here we go. Up and over how many? Or using the slope formula. What did we get for the slope of AB? When you're ready. Slope of AB, Jayla. What do you have? 2. Did you go up and over? Because it looks like you flipped it. What did you use? The y2 minus y1 or rise over run? Okay, so up, over. And what do we have now? Up how many? Over how many? 5. 1, 2, 3, 4, 5. Make sure you have, check your A and B again. Check your A and B. Make sure that's definitely 1, 6 and that's 7, 9. I don't want you to be off here. Going up and over. We'll come back though. There we go. Taylor, up and over.
Up 1 over 2.
Okay, 3. I have 3 over 6.
Well, I had that too.
Okay, all right. I'm doing it to make a point. Make sure you reduce it, please. All right, I do want it reduced, and I'll show you why in the next step here. So that's 1/2. We good on finding that slope? I don't want decimals. No, no decimals. Leave it as fractions. Leave them as fractions. Good question. Now find the slope of DC. I don't need to find the slope of the other two. I know it's going to be these two that should be parallel. So go ahead and find the slope of DC now. Change in y over change in x or rise over run. It's up to you. And up and over how many, or using your formula, whatever works. Told you we're coming back to you. Jayla? Yep. 10. 5 over 10. Good. Now this is why I want it reduced. Some of you, I hope not, but some of you might just have 3, 6, and 5 tenths and be like, they're not the same. Actually, they are. So reduce it at all cost. Your calculator does it for you. Okay, everyone all right in step 1? Use a formula. This was the slope formula. Maybe we'll have to use distance later. Step 2, right below it. Nice and organized for me. What did you just learn from the previous step? All right, so all this work we just did here came out to be 1/2 and 1/2. What did you just learn? That's what I want the next step to be all the time. What did you just learn from the previous step? All right, let's talk here. Rayan, what did we just learn here in step 1 by doing all this?
They are parallel.
Yeah, well, yep, correct. AB parallel to DC. That's what we just learned. How'd you know they were parallel? Because we're going to have to write a because here.
They
Why?
have the same slope.
Perfect. Because slopes are equal. So in all these coordinate proofs we'll do this unit, you show me a formula in step 1. Step 2, what did we learn from it? We learned they're parallel. All right. If they're parallel, is this a trapezoid now? Yep. So here we go. Step 3. Let's finish this bad boy. ABCD is a trapezoid. Because, Jesse, I'm going to go back to you because I asked you at the beginning, what was one property of a trapezoid? The only property?
They have the opposite sides of the same.
One pair of opposite sides are not the same, but
Um,
same kind of means they're congruent. They're not what instead?
parallel.
Okay, because one pair of opposite, I got to have that word in there, opposite, because of one pair of opposite sides are parallel. And there's a trap. There's your first coordinate proof. It's not the only one we're going to do today. So use a formula. What'd you learn from the formula? And then in this case, we could stop because it's already a trapezoid. Notice how organized it is, steps 1, 2, and 3. I know some of us don't have the best handwriting. I'm not going to be critical of that, but at least you can make it organized for me. Any questions here before we try out another one? All right, go ahead and graph the second one now. So we'll try to just graph it. Don't try and go ahead with the steps yet. Right. Connect them for me. We'll get going. What are we asked to show in this one? Isosceles trapezoid. Whoa, 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 whoa. We can't even do the isosceles part unless it's what first? A trapezoid. So we have to show it a trapezoid first. Forget about being isosceles. You can't show me it's isosceles unless it's a trapezoid first. So same way we just did before. We can already tell what the two sides that are probably going to be the parallel sides. So we got to prove it a trapezoid before we say it's isosceles. So let's do the slope of AR. Now I did this for a reason, Anya, just to remind you. What type of line is AR? I know that straight, they're all straight. AR is what type of line up there? Horizontal. Anybody remember slope of any horizontal line? Because it doesn't have any rise.
0.
0, yes. Any horizontal line has a slope of 0. So no work needs to be shown. I guess you could plug it into the formula. You're still going to get 0. And we can say the same for NO. Also has a slope of 0. Nice and easy. Step 2, going back to you guys, what did we just learn now? From step 1, what did we just learn? Because that's what I want your step 2 to be all the time. What did we just learn there? Let's try again. Jonathan, what did we just learn there? They're parallel. AR, parallel to NO. And how'd you know that, Jonathan? Because I got to put a because here. Because slopes are equal. Perfect. Good so far. All right, let's go to 3 now. Similar to the first problem, now we know NORA is a trapezoid. Because, and again, use your work from above. Don't make up something brand new. Look up above and tell me what you did. Because one pair of opposite sides are parallel. That's all you need for a trapezoid. Now we got to get an isosceles, huh? All right, we know it's a trapezoid. Now I got to turn it into, I'm going to ask you guys now. I went over 3 properties that are specific to an isosceles trapezoid yesterday. I want all 3 right now so we can decide on which one we're going to do. All right, I want all 3 right now. Just give me one of them. We went over 3 properties yesterday that are specific to an isosceles trapezoid only. Name one of the 3 here because we got to know them sooner or later. Calling for it there. Jesse, one property?
The base pairs are congruent.
What do you mean base pairs? Base.
Angles.
Okay, all right. And I'm just writing, you don't have to write these down with me. I'm just jotting them down. Base angles are congruent, only in an isosceles trapezoid. Yep. What else is true for an isosceles trapezoid only? Jayla? What are? Legs. Yep. Legs are congruent. And the final property I gave you guys, specific to an isosceles trapezoid only. Where am I going? Not here. There we go. We'll go with, yep, I'll get there sooner or later. Give me a second. Sydney. Oh, you weren't. Yep, that's right. You weren't here yesterday. Let's go. All right, Jayla, back to you. What? Diagonals are congruent. All right, so we're going to have to do one of these 3 right now. You do not have to do all 3. One of these 3 will make it an isosceles trapezoid. Can we get rid of one of these? Because it's going to be kind of impossible here on the graph to do. Anybody think of one I've already written down up here that you're like, there's no way we're going to be able to do that on the graph? And I'm going to eliminate it. Which one is impossible to do right now? Taylor? Yeah, there's no way you're going to show me those base angles are equal using distance, midpoint, slope. So that's out. So we just got to make a class decision now. What do you want to do? Because both are doable. We just got to make a class decision. You want to do legs congruent or diagonals congruent? Anybody? Legs, you got it. Let's do the legs are congruent. So here we go. Step 4 now. We got to extend our proof. We're going to show the legs are congruent. Ooh, I'm going to need a new formula for that, aren't I? Slope ain't going to do that. What's going to do it instead? Distance formula. Yep. So we're going to need to use the distance formula on AN. And we're going to need to use the distance formula on the other leg, RO. And keep in mind, they should be equal. All right? This isn't like a yes or no, it's isosceles or not. It is going to be isosceles. You got to show me why. So go ahead. I'll give you guys plenty of time. Use your distance formula, and hopefully you plug it into your calculator, and they come out to be the same. So we know it's a trapezoid. Now we're proving an isosceles by showing the legs are equal. Plug it into the formula, then you go right to your calculator and plug it in, and hopefully you get the same value for each. You need to see the homework before you leave, Joe. All right, work on this. I'm not worried about it right now. Work on this. Are we looking 5? 5 for each, right? Hope. Again, you get different values. Something went wrong. You should get the same values because this should be an isosceles trapezoid. All right, let's keep following our rules. Step 5, you got to tell me what you just learned. You're not ready to say it's isosceles yet. What did you? Anytime you use a formula, the very next step is what did you learn from that formula? We did not learn it's an isosceles trapezoid yet. What did we learn from the step above? In your own words, what did we just learn from the step above there? Zoe, what did we just learn here? Is what? You use distance though, so why would they be parallel? Okay, that makes them what? There you go. So AN congruent to RO because distances are equal. Anytime you use a formula, very next step, tell me what you learned. Are they parallel? Are they congruent? We'll get into perpendicular later on in the unit. And then finally, all right, now we can say ABCD, or NORA, sorry, NORA. NORA is a isosceles. If you want to abbreviate, you can. I'm fine with that. Isosceles trapezoid because what property did we use? What property of an isosceles trapezoid did we just use? Zoe, back to you. We showed the because legs are congruent. Done. All right. You don't want to say diagonals congruent. We didn't do that. You don't want to say base angles congruent because we didn't do that. So everyone are right here on a coordinate proof. We're going to be doing these for every figure in the unit. All right, every figure, just not today. All right, last thing I want to do with you, I want to show you a special segment inside the trapezoid. Special segment inside the trapezoid. And to do that, you're going to need some midpoints here. And that's why I gave you the midpoint formula. So I'll give you guys a couple minutes right now. We're done with the coordinate proof. We're done. Find the midpoints of the non-parallel sides. All right, NA and RO. Find the midpoints of those the legs. Find the midpoints of the legs. That's why I gave you guys the midpoint formula earlier today. And you can compare around your group. Going to call the one midpoint E and the other midpoint T. Add your x's, divide by 2. Add your y's, divide by 2. All right, let me get the midpoints from two people right now, and then I want them graphed. All right, I want them graphed afterwards. So let me start with point E, which was the midpoint of OR. What was the midpoint of OR here, which we're calling point E? Midpoint of OR, where are we going with that one there? I know I just did this one a minute ago. Sydney, do you have that one? Midpoint of OR. And good, make sure everyone's got that graphed. 5, 4.5, 5, 4.5. We're calling that point E. And then what about AN, the midpoint of AN, which we're calling point T? Where are we going with that one? Juliana, what do you got? Yep, and good job. Everyone, nice work there. -1, 4.5. When you have those graphed, form a segment. Okay, form a segment with those two, TE. We have a new vocabulary term for that one. When you join the midpoints of the non-parallel sides in a trapezoid, when you join the midpoints of the non-parallel sides, that's called a, ready? Midsegment. Midsegment. And if you're ever confused, it's right in the name. It's a segment, mid for midpoints. It's a segment joining the midpoints. All right, and it has to be from the non-parallel sides. Before we end today, there's two things I need you to know about a midsegment. If you know it's a midsegment, there's two things. I'm not going to give it to you like usual. I want your help finding them. This should be a quick one. Anybody tell me the slope of EF? From our work today, slope of EF, we don't even need the formula. What's it going to be? It's horizontal line, so it's going to be 0. Yep. Wait, didn't something else come out to be 0? Didn't these two end up being parallel? I mean, end up being a slope of 0? So what do I know about all three then if they came out to be 0? All three are parallel. And what do I call NO and AR again? They were a special vocab term I gave you yesterday. The parallel sides of the trapezoid. I don't want to keep calling them parallel sides. What did we call them yesterday? They're called we had the legs was the congruent sides, but the parallel sides from yesterday, if you got to go back, Halo. Yep. The two sides that were parallel were called these. The legs were the congruent parts, but the parallel sides were the... Did I not give it to you? Bases? Did I not give that to you? That's my fault then. The parallel sides are called the bases. Okay, the parallel sides are called the bases. So if you go turn your paper now to where it says the properties of a midsegment. It is parallel. The midsegment is parallel to the other bases. Other two bases. Because remember, they all have the same slope, so they're all parallel to each other. All right, so now I have a property number 2 listed, though, don't I? All right, let's go back. Go back a page. We got to figure out what this other property is then. And you guys don't need distance formula because everyone can count these. I want you to find NO. How long is NO? How long is RA? The two so I want you to find how long the two bases are. Just count. We don't need distance formula here. Just count them. And then I want you to find what about the midsegment we just formed, TE. How long are all those three? The bases and the midsegment. Count them over. How about base NO? Base NO. What do we got for base NO here, Jesse? 10, good. I got 10 here. How about the other base, RA, the smaller one? The smaller one there, Alex? 2. And then how long was the mid segment when you counted it up? How long was the mid segment there? Juliana?
5.
Should have been 5. You went from -1 over to 5.
5.5.
You went from -1 over to 5. How many units is that traveling? How much? 6, right? Yep, -1, right? Over to 5. That's 6 units. Good. All right. I don't know if I think some of you can do this. Is there any way, if you knew the 2 lengths of the bases, how you can get to the length of the mid segment? I probably should have done another one, but do you see what I can do to the lengths of the bases to get to the length of the mid segment? Anybody see anything you want to try to throw out there, Keating?
Divide by 2, add 1. That's what it is.
What do you mean divide by 2 and add?
Oh, wait, no. I don't know.
Okay, that's fine. Again, I want to try to do something to the bases, both bases, and get to the mid segment. What's up, Aiden?
6 is like the middle value both numbers.
So it's kind of like the midpoint almost, right? So add the bases and divide by 2. Add the right 10 plus 2, 12 divided by 2, 6. That's how you find the mid segment. You add the bases and divide by 2. All right, so let's go back to our last property. So the last property of a mid segment, and probably the more important one, is its length is equal to half. What do we do with the bases again? So half the sum of the bases. So if I know it's a mid segment, its length is half the sum of its bases. All right, let's try one out before you guys try some homework problems on your own. I got an isosceles trapezoid here, and the mid segment is drawn in 2x minus 5. Let's start by finding x. And then we'll go y. So finding x. That's the mid segment. 2x minus 5 is the mid segment. You tell me what it should be equal to based on what we just wrote. What am I going to set 2x minus 5 equal to? What is the mid segment length equal to? Use what we just used above there. Here we go. Rowan, what's good? It's equal to
22.5.
What's that?
22.5.
Hold on, don't. You're going too far. Just how'd you get there?
Oh, I did.
You're just going advanced here for me.
45.
How'd you get 45? Go ahead.
Added the base, the sums of the base.
Yep, I just want to show everyone where all these numbers are. So we're taking half the sum of the bases, 32 and 13. That's where he's going. All right, everyone all right? Half the sum of the bases. Now you guys can solve. You will get a decimal here. Half of 45. And that's where you heard Rowan say 22 and a half. Go ahead and solve, and yes, you will get a decimal. It happens at times in math. $13.75. 13.75 look good. You add 5 and divide by 2. And we ready for y? I want to remind you this is an isosceles trapezoid when we find y. Start thinking about some properties in your head here. It's an isosceles trapezoid. Let me start here. Everyone's here. I got 72 here. I believe you can plug in 72 somewhere else based on your properties here. What do you know about the angles? Let's talk to me about the angles here. True, we'll get there sooner or later. Keating, what do you know about my angles of an isosceles trapezoid?
They're equal.
What are equal? Not all of them, but the
Base angle?
base angle. So that's why I said, hey, you could place another 72 and that's where it can go. Agreed? All right, now the final thing is, before I set up my equation, what about those two? What about those two? The 72 I just placed there and the 5y minus 2. Supplementary. Why, Jonathan? What did we call those again?
Alternate two.
Oh, my
same
heart.
side.
There you go. Same side interior. It's all right. It is embarrassing. I know. You're good. Same side interior angles. And they are
Supplementary.
good. Save yourself. So 72 and 5y minus 2 have to add to $1.80. They're supplementary. So we got 22. There you go. 22. All right, go ahead. Let's get moving. Use the rest of your time here. It's on packet pages 14, 15. Let me just take a